where it's got a rise time, it has an on time, tau, and it has a duration t. We're going to assume t fall is equal to t rise, tau rise. Magnitude A, and that's repetitive. Now, the truth is I went through the Fourier series expression to get the coefficients. Then what I did is try to take those and turn them into a functional forms that you understand, sinc functions. And what you ended up with, if you take this whole thing, and then you say this is my x of t, you end up with a Fourier series approximation of x of t be equal to the summation from n equals 1 to infinity of 2 times the magnitude of c of n. This is going to be the cosine series because it's the one that puts it in terms of a phasor form easily. Times the cosine of n omega naught t plus the phase angle of c of n. And here, c of n is equal to technically 1 over t, the integral from minus t over 2 to t over 2 of x of t e to the minus j n omega naught t dt. I didn't say this, but omega naught here is equal to 2 pi over the period. It's really 2 pi times the characteristic frequency, or the harmonic frequency, f naught. And anyway, I'm just putting that all down, and then I'm going to go to the next step and talk about what this thing actually, once I do all this, if we look at the envelope of these values, the values themselves, we get c of n is equal to, and if you remember this, there was going to be an a, right, times tau over 2, and then it's going to be times the actual sine of n pi f, well, let me get this way. N pi f tau over 2 times the sine of n pi f tau rise over 2 all over n pi f tau over 2 n pi f tau rise over 2. And there's also a phase term, e to the minus j n pi f, and then it's tau plus tau rise over 2. The phase term you can ignore. That's what you came down to, if you recall. Now I'm just putting this up here so everybody has a point of reference. You all remember that? We did that thing, we proved it by doing double derivatives of that, getting the Fourier series of the derivative series where we had impulses, and then reversing the procedure to get c of n by dividing by jn omega naught squared, right? All remember that? All right, I'm trying to get there. So when we look at this, really, right here, if we were taking a look at this series and we were talking about the Fourier components, you see how there's a factor of 2 c of n magnitude there, right? This is so important what I'm about to show you. Y'all with me on this? Now that means versus frequency, if you wanted to see the strength of that signal, now this c of n is in volts, if you square it would be the power. If you actually view this versus frequency, I'm going to put it here. This would be f, and this would be a logarithmic x, actually log of f scale here. So you basically get like 1, 10, 100, and stuff like this. And on this axis, you do 20 times the log. And a lot of times what they'll do is they'll take the log of the values of c of n, or 2c of n, because this is going to be the logarithmic of the coefficients that would be associated with the phasor terms. So it would be the magnitude of 2 times the magnitude of c of n, right there, divided by 1 microvolt. That means this unit would be typically dB microvolts, and that's what you saw in the homework. Do y'all remember that class? dB microvolts? You're just taking the value and divide by 10 to the minus 6 to put everything you're scaling together. Okay? Now, here's the way this looks. When you plot this thing, what you get is this. You start out flat. The height of this thing is going to be simply 20 times the log. Right? If you just take these terms and take the magnitude of it, take 20 times the log, the first thing is going to be 8 tau over 2. There's going to be a 2 there because of this 2 here. So it's going to be 2 times magnitude of A tau over T, pardon. Over T, right there. And that should be over T. That's where it starts, and it's going to stay there until I hit the first break frequency. That frequency will be pi times tau, or 1 over pi times tau rise. Let me get that down there. There's the laser. I put this in the notes too on OneNote. This frequency is going to be 1 over pi tau, and it's going to start falling at that point at a rate of minus 20 dB per decade. And then when it hits the second break frequency, which is 1 over pi tau rise, then it starts coming down at minus 40 dB per decade. Okay, I'm putting it all up there. I did this. You've got it on OneNote, but that's the way it goes. This is a logarithmic of the frequency axis here. That's 20 times the log of 2 times the magnitude of C of n over 1 microvolt there, and this is typical. This is the way it's done in EMC. So these are the plots you see. Now this is the envelope. What I wanted to say too is, last time I said this is, I knew it was 1 over pi tau, but I said 1 over tau. The problem is this, when you look at this right here, that's a sinc function, what I just circled. Do you see it, everybody? Now, it's when the lower argument goes to 1, right here. And this would be f naught here, by the way. And what we actually do is we combine nf naught and we just let that be f, so we ignore the discrete terms of it. We know it's going to be discrete. And we just look at the envelope, because that, if you can understand what the envelope's doing, then you get the worst case possibility. And here's the truth. What really happens is if we look at the magnitude of 2 times C of n, it would be doing this. It would be periodic. And then we'd go like crazy. Y'all follow me? So you would get this. This would be the envelope. It would be the maximum possible value. And that's what we always use when we do EMC analysis. Is everybody with me on this? Now, with that thing, you can think about this. If I wanted the value of this function, or I wanted the value of like the 8th harmonic, suppose it was up here, 8 times f naught, all right? What I would do is I would take 20 times the log of 2 times the magnitude of 8 times the duty cycle, tau over t, divided by, and this would be divided by 10 to the minus 6, right? To make it dB microvolts. Then I hit this point. Now at that point, I know it starts coming down. So if I just picked out, suppose I had a value here, and I'm just going to call that f1, and I want the value of this signal right here. What I would do is say that signal would be 20 times the log, right here, of, 20 times the log of 2a tau over t, the duty cycle, over 10 to the minus 6, minus, now listen, 20 times the log, and here's what you do. You see how this is 20 dBs per decade? If I went a factor of 10, if this is 100 megahertz and this is going to be equal to 1 gigahertz, then I'd be down just 20 dB. You all see that? But if I don't go a decade, it's something less. So the way you get that is minus 20, then you take the frequency you land at, f1, over the frequency where the break occurred, which would be 1 over pi tau. Y'all with me? Now, if this happens to be 1 over pi tau, 10 f1, then you're exactly 20 dB. Everybody follow me on this class? I mean, if f1 is 20 times this, then it would be, or 10 times this, then it would be log of 10, which is 1, would be minus 20b. If it was 100 times, then the log of 100 would be 2, then it would be minus 40 dB now. You all with me? Everybody understand this concept? Nathaniel, can you see it?
Yes.
I can't see you here. All right, now, what happens if it's not here, though? What if it's out here? Y'all follow me? And we're worried about the worst case. In actuality, it might be 0 if we're at a relative null. You follow me? But don't worry about that. What you really want to worry about is, because these are actually going to be discrete lines. This is the envelope of the sinc functions, but I'm just telling you this right now. What you're always worried about is the maximum possible value, because that's the one you always work against. Even though if it doesn't occur, don't worry about that. Well, if it's out here, if it's not at f1, if it's at f2, then what we do is this. Now, you all follow what I'm doing here. Now I want what this value is. So you can forget about that. I want to know what it is right here. Okay? So listen to me. You have to go ahead and you have to take minus 20 dB times the log of this frequency divided by this frequency. That's the range you span. So then this would be 20 times the log of the frequency you end up at, which is 1 over pi tau rise, over the frequency you started at, which is 1 over pi tau. Are you with me? Now I'm right here. I'm at this point. But now I'm going to start going down by 40 dB per decade, because that's when the second one kicks in. Y'all with me on this class? That's when the second sinc function right here kicks in. And then I would have to subtract, now it would be minus 40 times the log of the frequency, in this case f2, that I ended up with, over the frequency I started. And then if you have a filter, what you have to do is find out what the dB loss or gain of the filter is and multiply it by the input signals envelope to find out the actual value. Now that was the whole basis of all the problems I gave you. I'd like to do a few of the problems because this is so important in the real world. Does anybody have one in particular they'd like me to do? Or do you want me to pick one? They're all good. Anyone? Did y'all see them? Right? They were up, right? William, do you have one? Or Jack? Or Nathaniel? Or Tyler? Or anybody? Han, do you have one? What's that?
It started echoing. Yeah, I was gonna find one.
Well, first of all, you're going to have a waveform. If you're going to have a waveform, we're going to have something like this. It's repetitive, right? It's a square wave, and we got a rise time tau rise. We need that. We need the on time tau over the actual duty flow over capital T, the duty cycle. We need the magnitude A, and we need the characteristic frequency, the periodic frequency, F naught, which is 1 over T. That would be the actual square wave frequency. Does anybody, which one do you want me to do with?
Could we?
Did you all do these or not? Did you try them?
Could we do 3.2.3?
Yeah, give me the specs. What's the rise time?
Okay, so the rise is coming in at plus 20, and then it goes.
Whoa.
Okay.
No. The rise time isn't at plus 20. It would be at 20 nanoseconds. Which one?
This one.
All right. Well, first, what they've got here is not a rise time.
Yeah.
They have a waveform shape, right?
Mm-hmm.
And then they have a filter. Why don't we come back to that one?
Okay.
Go up. Why don't we try determine the magnitude of the output of the system? This is 3.2.2.
Okay.
And they give it to us. All right. Let me draw this. So what they'll do is this. This is 3.2.2. And they have this drawing already for you. What's this frequency?
That's 20 times 10 to the 6th. Yeah.
Is that versus omega?
That's omega 2, or that's equal to omega 2. But yeah, that's omega.
And then what's this frequency, the second one?
Oh, I'm sorry, that was the second one. Omega 2. Omega 1 is 10 to the 6th.
Okay. So it's a megahertz.
Yeah.
Omega, this is omega, not F. It would work the same way. So this is going to be 10 to the 6th, and this is versus omega. Now what's the other one here?
20 times 10 to the 6th. And that's omega 2.
All right. And this slope is going to be minus 20 dB per decade. This is minus 40 dB. What's the starting point here?
120 microvolts. dB microvolts.
dB microvolts.
Yes.
Yeah.
Sorry.
So that's dB microvolts. And what do they want?
Determine the magnitude of the output of the system shown in figure 3.2.2, which I believe is this one. Oh, no, that
It's
one.
this. No, it's this.
Oh, yeah.
All right. Here, let me just show you what else he has. So that's the actual waveform of the input of the system. And look, this right here, 120 dB microvolts, what that is, 120 dB microvolts is equal to, right there, is going to be 20 times the log, right here, of the magnitude of 2A times tau over T. That's the duty cycle over 10 to the minus 6. So if I asked you for A, if you knew the duty cycle, typically 50%, 0.5. 0.5 times 2 is just 1. So 20 times log of A over 10 to the minus 6 is 120. You could back out what A is. Do y'all follow me? Did he say anything about the duty cycle in there, William?
No, not that I see.
All right.
That I can show you.
That's all right. So consider this x of t. I'm going to slow down. I want to make sure everybody sees this. If you have a question, please ask. Y'all understand this? There's a square wave going into a filter. Now, the way we represent it is we're going to put x of t. You could use x of omega. Doesn't matter. And you have some filter, but here the characteristic h of omega is versus frequency. And what they actually want is information about the output. Now, what are they asking for?
The magnitude of the output of the system shown. So
They want the entire output.
yes.
Okay.
The magnitude.
Now, this is the frequency, this is the input, so call this, if you will, this is a plot of x of omega. It's actually not quite x of omega, it's 20 times the log of the magnitude of the coefficients, right, for a phasor coefficient for the 2 times magnitude of c of n. All right, don't worry about that, but this represents the input waveform. Now, that filter characteristic is given. It's versus omega. And here, take a quick look, it's coming down, or no, it's going up at a rate of minus or 30 dB, or 20 dB per decade, and it starts at minus 30 dB. So here's what this filter looks like. This is h of omega. And what they got here is it starts at minus 30 dB, and it goes up. The slope of this thing is going to be plus 20 dB per decade. And what's the lower frequency?
It's 10 raised to the 5.
10 to the 5th.
Yeah, 10 to the 5th.
So it's a tenth of a megahertz.
Mhm.
With me? This is versus omega 6, so it's 10 to the 5th. Well, you guys are smart. I know it. Forget y of t. Let's just take a look at the magnitude of y of omega. That's going to be the magnitude of x of omega, right? Times the magnitude of h of omega. You all agree with that? I mean, that's fundamental, right? Know the transfer function multiplied by the input, you have the output. In the omega domain, if you took an inverse Fourier transform, you'd have it in the time domain. If it was a transient waveform, if you did a Fourier series inverse, then you would have it a Fourier series representation. But you all agree with me there. Just think think circuits, AC circuits. You know a given frequency, you find out what the transfer function is in omega, you can get the output by multiplying input by output. So in this case, this is my waveform, x of omega, and I got to multiply it by that, don't I? Now if you multiply that, and if I did it logarithmically, if I take 20 times the log of y here, over 10 to the minus 6, that would be equal to 20 times the log of x of omega over 10 to the minus 6, right? Plus 20 times the log of h of omega. Now I'm going to take magnitude of all these. Y'all with me? If you take log of a times b, it's log of a plus log b, the 20 outside. Everybody with me in this class? Please make sure you are. All right. We got this. That's this, don't we? Y'all follow me? It's not a mathematical statement, it's a sketch, but frankly, it is a mathematical statement. We could adapt any curve you want to that. That's a mathematical statement of what that 20 log of magnitude of x omega over 10 to the minus 6 represents. Now it's multiplied by this, so I have to add this to that, right? Can you all see that? What? Yeah.
How would you add a graph in dB microvolts and one in regular dB?
No. You've got dB microvolts, you divide this whole thing by 10 to the minus 6. So you just leave the 10 to the minus 6 here at the input, because the input's in dB microvolts. This one's just the log of h of omega. You see that? The 10 to the minus 6 stays there. Good point, though. All right, so what is this going to look like, the output curve? Just watch this and you'll see it. Y'all see that starts at minus 30 dB at 10 to the 5th, right? R starts, that's 10 to the 6th, so 10 to the 5th is down here, isn't it? Agreed, class? So I start at 10 to the 5th, I've got 120 dB microvolts. Now listen, you agree with me? That's what it is forever down that way, right? 120, and I got to subtract minus 30, so I have 90 dB microvolts. Do you all see that? Right? 120 minus 30 is going to be 90, correct, class? This should be in there. So you start at 90 dB microvolts, right? And what's the rate of increase? 20 dB per decade. Now just watch. So it starts at 10 to the 5th is where my drawing is going to start at. This is going to be versus omega. And this will be 10 to the 5th. I start right here, and I'm at 90 dB, and I'm going to go up at 20 dB per decade. Well, now just everybody look at this. Make sure you see this. Okay, you ready? From here to here, 10 to the 5th to 10 to the 6th, that's 1 decade. Agreed, everybody? A factor of 10. That means I'm going to go up by 20 dB, because it's 20 dB per decade is the slope of that line. So if I add 20 to 90, what do you get? 110 dB, agreed? So now, at 10 to the 6th, I have 110 dB microvolts. You agree with me? Follow me what I'm doing? Keep going now. Now, at that point, this starts going down at 20 dB per decade, right? Yeah.
I don't quite understand why or how it works where it's kind of like what he was saying is minus 30 dB. You're subtracting it from 120 dB microvolts.
The fact is, when you have, if you look at this equation right here, y is equal to x times h, right? Take 20 times the log of that, but then you have to divide that by 10 to the minus 6, correct? Now this is the one thing I've got to tell you. You have to watch this. This will be in dB microvolts. This is dB. You all with me? The microvolt stays there in this one. This doesn't. It's still fine. You can add dB to dB microvolt. The micro just indicates the unit it was normalized to. All right? It was normalized to 10 to the minus 6. You don't even have to use a unit if you don't want to. But because we're electrical engineers, we use volts because it's common. Everybody with me? You could have just put a mu symbol there, but that's okay. Now, I mean, do you understand how I got to 10 to the 6th? All right, what happens then? Well, this one keeps going up at 20 dB per decade, right? But this one starts going down at 20 dB per decade. The net effect is what? 0. No change. You with me, class? You add one going up at 20 dB and subtract one going down at 20 dB, the net result is 0. It stays at this level. Agreed? All right, now, where's the next transitional point? at 20 times 10 to the 6th, right? Now this is important you see this, so pay attention. I went from 10 to the 6th, now I'm at 20 times 10 to the 6th. Now what happens?
It's down
Minus
to
20.
Now it's going to go down at, well, now you add minus 40 dB to an increase of 20 dB per decade, and that's going to be a decrease of 20 dB per decade, so it looks like this. William, do they have a drawing of this thing, of the solution?
I can see it.
No, go back, right there. Do they have it?
No, it's not what the paragraph says.
It says, determine the magnitude of the output at 50. We're going to do that, 50.
Okay.
All right. At omega equal 50, right?
Yes.
All right, now listen, just watch this, everybody. They were looking for the output up here. When omega is 50 megahertz. That's radians per second, by the way. All right, how do you get that? Now, this is such a good question. Well, you know the value here is 110. Does everybody understand how I get it? Now you got to figure how far it dropped from this point to this point. Here's how you do it. And I might add something. This stuff is so valuable to you. When you're going to take your your electives, if you're doing anything, well, just about everything, with creating real, high-speed electronics, EMC, radar, this is just used all the time when I'm showing you this type of analysis. So now what we end up doing, remember, I want the level of the output right out here. That's what I'm after, I'm wondering about. So I know the level of the output at 20 meg, right? And I know that's 110. So I say, am I actually Y out? Y at omega equals 50 times 10 to the 6th. Magnitude of that is going to be equal to, starts at 110 dB microvolts, right? Then I subtract 20, right? Because now it's going down to 20 dB. And what's the value going to be? Well, 20 times the log of the upper frequency, that's where I want the value at, minus the frequency the break, or divided by the frequency the break started. So it's 20 times the log of the ratio. The upper frequency is 50 megahertz, right? Or 50, I'm sorry, radians, 50 times 10 to the 6 radians per second divided by 20, right? And you can see that the 10 to the 6 cancel, so I have can somebody just do this? Take 20 times the log of 5 halves, 2.5, that I don't know.
7.95?
Yeah.
Oh, but I didn't subtract it from the...
So it's 110 minus 7.95 dB microvolts. And what's that actually?
102.05.
Is that what it is, William?
That's what my calculator...
I mean, what the book has.
Oh, sorry. Yes.
All right, you all see what I did there? That's the way to do these problems. Now, they gave us a picture of the H of omega, but generally an H of omega is gotten from a circuit. You can find out functionally how it varies with omega by just getting the transfer function. Now there's another problem. I want to do these because these are so important, and this is really MC. This isn't just the well, that's about the bandwidth. No, this is the way it really works. All right, so keep going down.
That's the last. You want me to go up?
Wait, isn't there another one?
It stops there.
All right, well, I'm going to give you a few more. Let me create one. I gave you a few where you had to calculate the Fourier coefficients using the derivative method. You all know, catch those? I'll probably ask you something about that. So you have to make sure you know how to do that. And it's not hard at all. Just do a few. You'll see it's trivial compared to the old way. of integration by parts. And I don't know, and I personally don't like integration by parts.
There's one where it's the Fourier, the series expansion of a waveform.
Yeah, there's a lot of them.
Oh, okay, I didn't know if you wanted one.
Those are early ones, right?
Yeah, yeah.
I gave you a whole bunch, but first, before we do that, let me give you this. Suppose I give you this, and this is a typical kind of problem that I do. I'm going to say, I have a waveform. I don't even draw them usually. Like this, magnitude is 5 volts. Rise time is going to be 20 nanoseconds, right? The actual duration over the period is 50%. So this is called a duty cycle. Is going to be 0.5. That means it's on half the time. That's all it means, really. Then if I take a look at this, and I'm going to say the fundamental frequency is equal to 10 megahertz. All right, now that's not a bad clock. All right, it's a low frequency clock. Nowadays, don't we have computers that are clocking at a gigahertz plus, right? So this is fairly low frequency. Do you all agree with this? We're going to take this, we're going to analyze it, but we're going to put this waveform into this circuit. This is not generally the way it's done. But we're going to take that as the input x of t, and our circuit is going to be this. Here we're going to make R equal to 10, say 10k ohm, and C is, say, 1 microfarad. That's a big capacitor. And what I want is information about the output. So here's my output Y of t. Now y'all follow me. That's the waveform that's going to get plugged in here on the input, and I want information about the output. Y'all with me? So the first harmonic is 10 megahertz. I don't know about you, but I'm being plagued by a whole bunch of things that targeted advertising, asking me if I want to lose 25 pounds, asking me to re-up my car warranty is expired, and no matter what I do, blocking numbers. I've done everything short of changing my phone number, but they keep coming. And they're coming now from 334, 844 numbers. That's Auburn University's internal number. Y'all follow me? So they're spoofing at you. I complained about that to a guy over in, really in network services, but in a guy, and he said there's nothing we can do. This is voice over IP stuff. Apparently you can spoof this all with all these things. Okay. So we're after that, and here's what I want. I want the output here of, say, I want Y of omega here, or better yet, I want the output signal strength of the, so I want the output signal strength of the 8th harmonic. Okay. So, here's how we do it. First of all, if this is the fundamental, the 8th harmonic, all right, would be equal to 80 megahertz. Are you with me? Follow me on this, guys? When I say F naught is 10 megahertz, it means 1 over T is 10 megahertz. You all follow me? Correct? Y'all with me on this, guys, everybody? All right, let's keep going on this, because this is fairly straightforward. First, we take a look at this waveform, and we draw it in terms of that frequency versus 20 log of the magnitude of C1 times all that stuff. But one thing we do know is when we do this, we'll have this curve no matter what. For any type of rise time, fall time, given duration thing, we're going to start off with a value of 20 times the log of 2 times the duty cycle, which is 1/2, right, times the magnitude of A, which is 5. And we have to divide that by 10 to the minus 6, right? So that's where we start right here. Can anybody give me that? Let's see, it's really what? Log of 5 over 10 to the minus 6 10 to the 6 up top, so it's 120, so it's about 135, 136 dB microvolts, something like that. You're going to have to do it for me. It's log base 10, by the way. Remember that, not base C. You calculate
133.97.
That's about right. 133.97 dB microvolts. That's the level it starts out. This is the input signal. This is just input, so call this 6 of a meg. Okay? Now, where's the first frequency it breaks at? 1 over pi tau, right? So now, William, or anybody else with a calculator, tau is what? Tau is this, right? What is this? Well, how do I get it? I know F naught, right, is equal to 10 to the 7th hertz, right? That means the period is 1 over F naught is 10 to the minus 7th seconds, right? Correct, class? And if the duty cycle is 50%, it means tau is equal to that divided by 2, or it's 5 times 10 to the minus 8 seconds, or really 50, right? 50 nanoseconds. Agree, class? Can you all see? Can William, can you see it?
Yes.
Okay, y'all good with this? All right. So, William, take 1 over pi times that and give me this frequency right here. This is going to be versus F here, not a menu.
It's going to be 6.37 times our mega.
Times 10 to
Megahertz.
the 6 hertz, right?
Yeah, 10 to the 6 hertz, yes.
All right, matter of fact, let's not do the 8th harmonic. Let's do the 15th harmonic. I just decided to go up. So we're going to go actually the 15th harmonic. So we're going to say F15, which is going to be 15 times 10 to the 7th hertz. It's 150 megahertz. You with me? All right. Now, at that point, the input signal starts coming down at minus 20 dB per decade, right? Everybody? It's going to keep going down until what?
Till 1 over pi times tau rise.
Right, until this point. Right here. And that's going to be, this point is 1 over tau rise times pi. What is that point? Now, let me put it down this way, because I'm kind of... Where's this frequency? Can you give it to me? 1 over pi tau rise. Tau rise, I made 20...
20 nanoseconds?
Yeah, so what is it?
Sorry.
And that's, by the way, the fourth one. That's, after that point, it's basically dead. It's going 40 dB per decade. 1 over 20 times 10 minus 6, or 1 over 2 times 10 to the minus 8.
So that's going to be 15.92
Okay.
times 10 to the, or kilo.
15 point what?
15.92.
Megahertz, right?
Yes.
10 to the 6. You agree, class? Yeah. Now, at that point, it's going to go from 20 to minus 40 dB per decade. Are you with me, everyone? Okay? All right, are you with me? I'm trying to get a good read on you. By the way, maths make it hard, because I can't see what you're really looking at. I see eyes, and eyes sometimes are, I don't know what that means. Okay, so I have this. Now, what do I really want? I want the value of this signal strength at the 15th harmonic, which is 150 megahertz, right? So if this is right here is 15, and this is 150, matter of fact, that's a little high. I'm just going to tell you where I want it for you. I'm going to just say I want it at 25 megahertz. 25 times 10 to the 6 hertz. That's where I want the output. I don't want to mess around with these 8, 9, 10 harmonics. That's how they do it in the real world, but I'm just going to pick a frequency because I don't want to go too far. Are you with me? So the first thing I need to do is find out what the signal strength is at that frequency right here. Right there. And the way I do it, I bet you a lot of you know, what am I going to do? Okay, I'm gonna start here, right? Agree? This is just the input, not the filter itself. You agree, class? So I start there, and what is that, 133.9? So call it 134. 134 dB microvolts, right? Minus what? Now take a look. 20 times the log of what? Well, the frequency I wanted at, I put 25 megahertz is way out here, right? 25 megahertz is here. So I know I'm going to go through this region where it's dropping to 20 dB per decade. You all with me? So how much did it drop? Well, I got to take the upper frequency it stopped at, which is 15.92 megahertz, and divide it by the frequency it started at, which is 6.32. Isn't it, William?
Yes.
All right. Now I'm right here. Don't worry about the value. Now I'm at this point. You agree? Y'all see this, guys? I've got to go from here all the way up to 25 megahertz, right? But now it's coming down at 40 dB per decade. So now I have to take this and I'm going to subtract minus 40 times the log of the frequency I end up at, which is 25 megahertz. That's arbitrarily selected by me. I could select any frequency I want. So it's 25 megahertz over the frequency I started at, 15.92. Right? And that would be the signal strength value at 25 megahertz. So that's going to be the magnitude of X. F equals 25 megahertz.
I got 118.2.
And you got this value and subtracted this value from it.
Yes, and I put the units in there already.
And you put a 20 and a 40, right?
Yes.
Okay, can anybody confirm that? Just so.
And I subtracted it from 134 already.
So what'd you get again?
118.2.
dB microvolts, right?
Mm-hmm.
Y'all with me? That's the level of the input signal strength. Now we're going to find out the effects of the filters. So the first thing you do is find H of omega. So, or H of S, but H of omega, probably I better say that. It's really going to be N omega now, but just leave it as omega. You don't need to worry about it. So when I do this, what is the impedance of the capacitor? It's 1 over J omega C, correct, class? You agree? Impedance is 1 over J omega C. So if I want the output input or the transfer function, H of omega, which would be Y of omega over X of omega, then it would be 1 over J omega C over 1 over J omega C plus R. Now realize the only thing I've done there, is simply done a ratio of impedances. It's a simple voltage division. Do you all agree? We're going to talk about output voltage. So if I multiply top and bottom by J omega C, I get 1 over, it depends how you want to do this, over 1 plus J omega R times C. Agreed? With me? Jack? Jake? Are you okay with this, everybody? All right, now I need to evaluate this where? At what value of omega? 2 pi times 25 megahertz, right? Because that's the frequency I'm looking at, right? So now I have to go and I have to say, well, H, right, will be equal to, and this is at the upper frequency, would be 1, I'm going to need your help, William. 1 over, and do me a favor, get the magnitude of this whole thing. 1 over the magnitude of 1 plus, and then it's going to be J times 2 pi times 25 times 10 to the 6, 25 megahertz, times R times C. Well, R is 10 to the 4th, C is 10 to the minus 6, so that's 10 to the minus 2, isn't it? And I need the magnitude of that. And what do you get for that? It's going to be about 1 over 2 pi times 25, 1 over 50 pi 10 to the fourth. So this is approximately 1 over 50 pi times 10 to the fourth, whatever that is. You can go ahead and do it, but this value is going to dominate. You have to square this term and square 1 and add it together and take the square root. Don't you, class?
I got 636.6 times 10 to the negative 9. So,
Times 10 to what?
negative 9.
Oh, I got that.
Yeah. I did both.
Look, if you take 10 to the 6 times 10 to the minus 2, that's going to be 10 to the fourth, right?
Mm-hmm.
So I've got 25 times 10 to the fourth, so I got 50 times 10 to the fourth. So it's 5 times 10 to the fifth divided by pi.
No.
No, something's wrong with that.
Let me see.
Jack?
What did you say you got, Clothing?
I got 636.6 times 10 to the negative 9.
So I got 2.
You did?
Yeah.
Get 636 times 10 to the minus 9?
Yeah.
Okay, that's 0.636 times 10 to the minus 6, right?
Mm-hmm.
Yeah, that's believable. But you can check that. Just do this for me. Take 1 over 50 pi times 10 to the 4th.
I did that as well.
Is this
Yeah, it was the same. I got
Okay.
both the same.
Then I'm convinced that's right. Just didn't look right to me. So now what you do to get the output right here, I take this output value. What I want to get what the output is at that frequency, the magnitude of the output, and this would be at f equals 25 megahertz for the filter I've gotten, which is this value, 118.2 dB microvolts. Then it's going to be, and now it's technically a plus 20 times the log. Now, there's a plus there because the filter, you don't know if it's going to increase or decrease, right? When you multiply log x times h, it's log of x plus log of h, right? And there's a 20 in front of it, so it's going to be log of h. And h is, what is that again, 0.6, is it 36?
Yes.
Times 10 to the minus 6, right?
Yes.
All right, go ahead and do that. What did you get? You're going to see my point.
I got negative 5.72.
After you add it to this?
Yes.
Okay, check that. Minus 5, wait a second,
0.72.
0.72 dB microvolts. That's virtually nothing. I mean, you're into the noise, so to speak. All right. So this filter right here basically kills the output at that frequency, if you were interested in it. I'm just showing you with the filter. Filter doesn't have to do that. Filter could increase it or decrease it. Remember, any of these, if you have an amplifier system, you could get a boost of 20, 30, maybe 50 dB, so at a given frequency. But nevertheless, this is how you always figure out what the output is for a given frequency. And most of the times when you deal with digital circuitry, I'll just tell you this, I've got about a minute or two left. Almost always, what you're dealing with is something where they're worried about values of voltage on lines or electric field transmission at very specific frequencies. Because there are laws called FCC, Federal Communications Committee here in the United States that dictate this. And these regulations, if violated, you'll pay a horrific fine. You can go to prison and everything like that. FCC regulations also control everything that deals with hospital stuff. If you've ever gone to a hospital, you probably can't use your cell phone in areas where there's ICU and stuff like this. They want to make sure they're shielded. Has anybody ever done this in a hospital? You can't do it. I was in ICU for several days, and I learned that you can forget about cell phones. Thank God they had internet, but that was the only way. And there's another organization called CISPRI, that's European, that governs all the frequencies allotted in Europe as well as the voltages. Europe has pretty much the same frequency allocation as we do in terms of power levels or voltage levels at given frequencies and amount of radiated emissions and things like this. Here's the real difference. Europe has a much different frequency. It's 50 hertz. We're 60 hertz. Europe also has a voltage. We have 120 RMS roughly, 117, right, in the lines. They have what, about 205, right? What is it? 270? 207, you mean, right? It's hot. Where are you at? What country? All right, so Ethiopia's on the European. They got a 50 hertz cycle. Okay, and you're going to find out those are ubiquitous. One of the two values of voltage and frequency is everywhere in the world. All right, and the emission standards pretty much are the same. But here's the problem: when you create a product like this, all right, they test these things.